So such methods are actually predecessors of finite element method. So from this, one can see how finite element method can develop organically. So, so at first, let's start with a differential equation. Okay. And for the time being, let's take the example of a beam element. Sorry, not a beam element, a bar element. So this is the basic differential equation, and let's say it comes with boundary conditions. Okay, so we are talking about a situation where the left end of the bar has been fixed, and let's say this is the axis of the bar, and there I'm applying a concentrated force P, and across the bar there is a distributed load Q of x. Okay, so so these are the boundary conditions, of which the first one is called essential boundary condition, and we have explained in the earlier classes why this boundary condition is called essential boundary condition. This is also in differential equation term, it is also Dirichlet boundary condition, and this one is Neumann boundary condition. So what is Dirichlet boundary condition? Dirichlet boundary condition is actually on the variable itself on some boundary, and when that boundary condition appears on, let's say, the normal derivative. So you see, normal to the surface over here of the bar is x-axis. So the normal derivative of u with respect to x at any given value of x, that is what is known as the Neumann boundary condition. Okay. Also in finite element term, this one can be regarded as essential boundary condition, and this one can be regarded as the uh, natural boundary condition. And in addition, this can also be called as the kinematic boundary condition. That means it is a boundary condition on the deformation, and this one is a traction boundary condition. Basically, if this surface is traction free, then p value should be 0. So this is a traction boundary condition. This is the kinematic boundary condition. Now, why is this boundary condition called essential boundary condition? It's because you are supposed to provide this such boundary condition, this type of boundary condition, at least somewhere at the boundary. I mean, you cannot solve the equilibrium of this bar. You cannot solve the equilibrium of this bar unless you specify the value of u either at the left end or the right end. Okay. I mean, then if you have a solution, so we have seen for bar elements or even for spring elements, let's say with two nodes. Okay, so if there are u1 and u2, the difference of u1 and u2 is something which can be determined from the forces that are being applied. Of course, if the bar is in equilibrium, the two forces f1 and f2 should be equal and opposite, and then delta u can be determined as let's say f2 equals minus f1 equals f. So it is going to be f divided by k for a spring element, a spring element. Now, if it is not a spring element, if it is a bar element, then K is actually EA by L, linear bar element. So all of this we have seen. Okay, then we cannot determine U1 and U2. So unless I specify U1 or U2, one of them, I cannot determine the other one. So that's why it is essential. But let's see, if you are not solving an equilibrium problem, if you are solving a kinetic problem, then it is not mandatory for you to provide the value of U at any location. But you see, even if it's a dynamic problem, even if it is a dynamic problem, for example, you must be familiar with the oscillation of a simple pendulum. Okay, and this is what a pendulum looks like. Okay, a simple pendulum. So there is a weightless string and stressed by a dimensionless bob, which has the entire mass. Now, when we talk about one of the degrees of freedom, so that can be the angle that the string makes at any point while oscillating with the vertical. Let's call that angle theta. So the theta value may not be required to be given at any location. Okay, but the theta value must be given. See, in this case, everywhere the theta is the same. Theta is the same. Okay, but the theta value must be given at t equals 0. Not only that, the first derivative of theta must also be given at t equals 0. Okay. Now, such problems are called initial value problems. And this type of problems are called boundary value problems. Okay. Of course, the differential equation, if theta is much smaller than pi, okay, if theta is of the order of 4 to 5 degrees, then you can write the equation of motion to be okay. You assuming there is a free oscillation. Okay, and if theta is greater than let's say pi by 10, then this theta should be replaced with sine theta. So so that is the equation of motion, and in this case it is an equation of equilibrium. Okay, in either case this is a differential equation. The one is a second order derivative in space, the other one is a second order derivative in time. Okay, but you see, in either case you must provide the value of the primary degree of freedom either at the boundary or at the beginning of the motion. Okay, now you see, the temporal differential equation, the time dependent differential equation, they are called initial value problems. Okay, the reason being that if you look at the difference between the conditions that have been given when we are solving a boundary value problem, the boundary conditions are given, can be given at two boundaries. Okay, or rather it must be given at two boundaries. When it comes to time, the very fact that no one knows the future, you can only give the conditions at the beginning of the problem, hence the initial value problems. Okay. Achha. Now that is slightly diverted from today's topic. We are trying to have emphasis on traditional numerical methods for solving, of course, boundary value problems. So we are still interested in solving mostly the equilibrium equations. Okay. So so this is the differential equation. Okay. Now as we have discussed earlier, this q could be any function, and based on what type of function q is, the solution of u would differ. Okay, whether you are doing an exact solution or a numerical solution, u depends on the functional form of q of x. Okay, I mean, even if you take the example of finite element method, where you are trying to, even the very specific one, where you are trying to model the entire bar using a single linear element. Okay, which means u is a linear function of x, c0 plus c1x. But you see, for different values of c0 and c1, u is different function of x. And those different values of c0 and c1 would depend on what sort of function q is. I mean, whether q is 0.1 x squared or q is 0.01 x squared, not only would that matter, but also whether q is actually 0.01 x squared or 0.5 sine of x, that would also matter. Okay, so so that all I'm trying to say here, it's not just the closed form solution or the analytical solution, okay, where the nature of q matters. The nature of q or the very functional form of q, whatever that may be, that also matters when you are doing a numerical method, and you are going to get different solutions for different q's. Okay, now now let's say let's say you get a solution u hat. I shouldn't be putting u hat, I'm putting u tilde. Let's say this is your approximate solution. Now, until this point, until this line, we are describing everything in general for whether you are using a closed form solution or a numerical method, or if you're trying to get an exact solution or an approximate method. We didn't do any discrimination. Okay, but this line onwards, we are strictly talking about numerical methods and approximate solutions. Okay, so let's say u hat is the approximate solution that I'm going to get, that I'm trying to get. Again, from the vector and function analogy, let's say u is the function that I should be solving. What that is on what the differential equation is based on, and u tilde is a solution that I'm getting because I'm looking for a smaller subspace of functions. Okay, had I been looking in the global set of functions, that means all possible functions, there was a chance I could get the exact solution. But since I'm not, I can only get an approximate solution, u tilde. Okay, now as I mentioned that the difference between the two, again from the function vector analogy, would be regarded as r. Now if indeed u was a vector and u tilde was a vector, okay, of finite dimension, that would be a very simple job for you to define what a residual must be, right? So you simply take u minus u tilde. Okay, and that is very simple to understand, that this normal distance. Okay, so whatever u is, you take the projection, and this normal distance is the residual. That can be uh, imagined schematically, but you see, functions are vectors but not finite dimensional. Okay, so this is not how we can define a residual. And for defining the residual, this is what we would do. You see, if u was, I mean, if you choose u instead of u tilde, so everywhere within the geometry, Okay, this differential equation should be 0 because this differential equation is based on u. And if I could get the exact solution, for example, if q of x is x, then u should be a quadratic function of x. Okay, and if I do analytical solution, then I get the exact solution. And once I have the exact solution, okay, if I substitute that u in this differential equation, okay, then everywhere within the geometry, this would be trivially 0 because I'm using the exact solution. Okay, but if I restrict myself, let's say with a linear bar element, again I'm taking the example of finite element method, but this is today we are not exactly looking into the finite element method. We are looking into the methods that came prior to finite element method, and that describes the history of finite element method. So let's say if I try to get an approximate solution, if I only allow functions that are linear in x, obviously I'll be getting an approximate solution. And obviously, if u tilde is that approximate solution, it is not going to be this particular quantity e a u tilde double prime. It's not going to be plus q of x is not going to be 0 everywhere. Okay. In general, it is going to be a function, another function, r of x. You see, u tilde is also a function of x. This r you would regard as the residual. Okay. And let's say we are looking for u tilde in a smaller subspace. Then our intention should be to minimize this residual. How we can minimize this residual? Okay. So whatever u tilde in that function space, for example, in this function space, function subspace, I can imagine various other, let's say u tilde prime, u tilde double prime, various other functions. But as you can see, u tilde is the one among all of these functions which minimizes the residual. So since I'm already working in a smaller subspace, for example, with linear bar element in the subset of all linear functions, where clearly my exact solution doesn't belong to that subspace, then you should be eventually some C0 plus C1x. But then my job is to find out the C0 and C1 such that this residual is minimum. I mean, this can be one approach for solving or getting an approximate solution. Okay. And this type of methods are called weighted residual methods. Okay. And here goes your first assignment. And your first assignment is go through everything that has been discussed. I mean, today we'll do weighted residual methods and we'll take some examples. So everything from the class note that I've already shared, from that you're supposed to read, understand, and derive on your own. So that is your first assignment. Weighted residual method. Okay. So what is done in a weighted residual method? So let's say u tilde is defined as phi 0, which is a function of x, plus summation over I equals 1 to n ci phi I of x. This phi 0 and phi i's are the functions of x. Okay, they could be polynomial, they could be sinusoidal function or any other function. But here we are trying to get approximate solutions. These phi i's are called trial functions. Okay. Now there are some conditions to how you choose your trial functions. For example, phi 0 satisfies essential boundary conditions, which means if at at gamma u equals u star, that implies at gamma u, that means wherever at the boundary there is essential boundary condition, phi 0 is u star, which obviously means that other phi's, that is phi 1, phi 2 up to phi n, phi I equals 0 in gamma u for all I in 1 to n. So this is how you choose your trial functions.
স্যার আরেকবার এই ফার্স্ট কন্ডিশনটা একটু বোঝাবেন স্যার?
First condition is whatever is the boundary condition on u, okay, that directly applies to phi 0. So the job of phi 0 is to take care of the essential boundary condition. Okay, now phi i's could be any function, but they must be 0 at the boundary where value of u is given. Okay, বোঝা গেল কি?
ওকে স্যার।
তাতে করে কি হবে? Once you are done solving for u tilde, which is an approximate solution, it will also satisfy the essential boundary condition. মানে ধরা যাক at x equals 0, u is not 0 but let's say 1 millimeter. Okay, or let's say at x equals 0, u is 0, but at x equal L, u is 10 millimeter, let's say. So that means both the points, both the ends are gamma u, which is a possibility. Okay, there is no restriction that both boundary conditions cannot be directly boundary condition or essential boundary condition. So obviously they can be. One of them must be essential boundary condition. That's what is the condition. Okay. Now, obviously, then if I take an example where u0 is 0 and ul is 10 mm, and let's say L equals 1 meter. Okay. Now, if such are the boundary conditions, then phi 0 should be such that phi 0 at 0 should be 0 and phi 0 at L should be 10 mm. And all phi I 0 and phi I at L should also be equal to 0, because then both the ends are gamma u. Okay. Right now with this example, one end is a gamma u, the other end is a gamma t. Okay, so this one is gamma u, kinematic boundary condition, and this one is traction boundary condition, hence gamma t. But just take an example where both are gamma u's, that is this one. So in that case, phi 0 takes care of the essential boundary condition, but phi i's would be 0 at both the boundaries. এবার বোঝা গেল?
Sir, this phi I can be regarded as the arbitrary variant.
No. There is no concept of variation here. This is in this
like
case
phi
we are
at
not
both the ends. both the ends phi I is 0. So like
Yes,
similar to the previous
no.
cases.
First of all, please correct yourself. It's not both the ends where phi I is 0. The phi I is
Okay.
0 at gamma u. Okay, wherever gamma u, that means value of u is given. But that is the criteria for a function to be qualified for a variation. Okay, that doesn't mean whatever function satisfies that is indeed the variation. Okay, and let's say, I mean, you see, today's class you can think of is happening in a flashback mode. Okay, that means at this current instant there is no concept of variation. Okay, so these are some just functions. Okay, we are calling them trial functions. You can think of essentially they are exactly like the shape functions. Okay, but we are not bringing in the concept of variations. Of course, variations must satisfy the condition that they should be zero at gamma u, whether it is at one end or both ends. Okay, at a specific location in the boundary or everywhere within the boundary. Okay, but that is the condition for a function to be qualified for a variation. That doesn't mean that whatever function qualifies that is actually the variation. Okay, it's not. বোঝা গেল কি বলতে চাইছি?
Yes.
Okay,
Sir, means it
I know
has a
it helps
probability to
to.
be a variation.
It does qualify to be a variation, but it's not. Actually, whatever we will be doing today, we don't need the concept of variation. Okay, and I understand it's a new subject, and today we are doing a new topic, and there would be some instinct of relating that to what we already know. But just keep an open mind for today's class, because what we are doing today is entirely new. Okay, and you can think of this came before uh, we had the concept of finite element method. Anyways, so this is how we would choose the trial functions. Okay, আচ্ছা, এবার I'm clearing my screen. Okay, the next thing is, what is weighted residual? So we are now studying the weighted residual methods. You see, we are trying to get an approximate solution, which kind of looks like this: pi 0, a function of x, plus then c1, phi 1, another function of x, plus c2, phi 2, another function of x, and so on. And of course, satisfying the two conditions that we just described. Now, now for I equals, for I, for all I going from 1 to n, associated to every function, think of another function which would be the weight. Okay, I'm not saying that these two are somehow related. Okay, but the thing is, the number of weights should be the number of trial functions after phi 0. Okay, so once you skip phi 0, whatever the number of functions there is, okay, there would be exactly the same number of weights. So then, and these are all linearly independent functions. Now, what do I mean by independent functions? Let's say one of the functions is f1 of x is x, and f2 of x is x squared. Then f3 being, let's say, 5x minus 10x squared. These three are not linearly independent, because you can write this to be 5f1 minus 10f2, and eventually f3 minus 5f1 plus 10f2 equals 0, where the coefficients, let's say, if I can write it to be alpha 1 fi, alpha I fi equals 0, that implies alpha 1 is 1, alpha 2 is minus 5, and alpha 3 is 10. And this is a non-trivial set. That means all alpha is are not equal to 0. Actually, none of them are 0. And in such a situation, this doesn't form a linearly independent set, but we need linearly independent sets. Okay. So corresponding to each phi I, there should be equal number of weights. And for each weight, for all I, we would say this residual okay. So here we are not talking about any sort of variation. What we are talking about, it might look very similar, yes, because eventually the variation formulation and finite element method eventually evolved from this. Okay, but the concept is slightly different here. What we are simply saying here, you see, I know I am trying to get an approximate solution, which means this particular quantity, which is basically this r of x, would not be trivially 0. Okay, that means it's not in 0 everywhere between 0 and L, x equals 0 and L. It may also be non-zero everywhere. Okay, so it is non-zero, but I'm trying to put some sort of bound into it. It may be non-zero, but it's not, infinitely open. It is somehow bounded. Okay. So what we are doing instead is we are putting some constraints. You see, we still have, let's say, n degrees of freedom. Although we are solving it in a finite space, in this case n-dimensional space, so we have this many degrees of freedom. That means by changing these values, which are essentially coefficients, by changing these coefficients, we can have different function utility. Okay, so these are the degrees of freedom, and we need to somehow adjust this. Okay, which let's say minimizes this weighted residual. Okay, now what sort of function must wi be? Okay, there is a wide discussion on that, and that basically spans the range of all the weighted residual methods. But today we would talk about something called Galerkin's method. Okay, where wi's are essentially phi i's. Now, why do I need equal number of weights? Because you see, if I'm solving it in n-dimensional space, then therefore I have n coefficients to solve for. And how do I solve for n variables? From n equations. And by getting n number of weights, I'll be able to write this type of equation for n number. And thereby I'll be getting n number of such equations. Algebraic equation, because you see it's a definite integral, we are not going to get a differential equation. We are going to get an algebraic equation involving C1, C2, etc. This essentially turns out to be an algebraic equation in all CIs. Okay, and we need n such equations. Therefore, we need n such weights. Okay, to solve for n coefficients. Okay, so Galerkin's method is a special type of weighted residual method where we use the trial functions themselves as the weight. Now, what is the idea behind choosing these weights? Okay, or for that matter, okay, again, the condition on this trial functions are that they should be linearly independent. Now, let's take the example of Galerkin's method. Okay, where does this idea come from? That you multiply your residual, okay, which is a differential equation itself, with the trial function and integrate that and equate that to 0. Where does that come from? You see, if in Galerkin's method, instead of working with a subset VU of the global set of functions, which we are actually doing because we are doing an approximate solution, that's where we are over here. But instead of choosing a subset of functions, okay, if we were to choose all possible functions, that means there should be infinite number of such phi i's, and for infinite number of such phi i's or wi's for that matter, which are linearly independent, if this residual turns out to be 0, that only means that this residual is trivially 0 for all values of x. Okay, so the thing is, obviously, that means we would be getting an exact solution if the set of functions in Galerkin's method were the global set of functions. But if I'm working with a subset of functions, okay, with a limited number of C1, C2, C3, etc., then obviously I'll be getting an approximate solution. Okay, but the thought behind this is, let's say if I keep on adding more and more terms to this expression, okay, then by that what I would be doing is I'll be increasing the dimension of this subset of functions, and with that, since the global set actually gives you exact solution, by increasing the dimension you are actually approaching the accuracy, and there is an adequate number of terms, finite terms. Okay, so there is a possibility that you can have finite number of terms in this expression and get an adequately accurate solution, adequately close approximate solution. Okay, so there are two things. One is, as you keep on increasing the number of terms, you approach accuracy, and number two, you in order to have a reasonably accurate solution, you need not go for the global set, you can still go with a smaller subset. Okay, এই অবধি কি বোঝা গেল?
Yes, sir.
স্যার ওই মাল্টিপ্লিকেশনটা কেন হচ্ছে আরেকবার বললে ভালো হয়, মানে ওয়েটেড রেসিডুয়ালের সঙ্গে ডিফারেনশিয়াল ইকুয়েশন।
কি বললে বলো, আরেকবার বলো।
ওই ওয়েটেড রেসিডুয়ালের সঙ্গে ওই ডিফারেনশিয়াল ইকুয়েশনটা যে মাল্টিপ্লাই হচ্ছে মানে ইন্টিগ্রালের ভেতরে, মানে ওইটা আরেকটু যদি বলেন একটু ভালো।
আচ্ছা আচ্ছা, ঠিক আছে। You see, this u has n trial functions, so there would be coefficients to each trial function, that therefore there are 9 variables. That means by varying those quantities c1, c2, see, these are some fixed function. Okay, you are not changing the functional form of them, but these coefficients can change and therefore give you infinite number of functions. Okay, but then they can only change in n dimension, and as we have discussed, your function space is infinite dimensional. Okay.
Yes, sir. Yes.
So, firstly, that ideally, if you took infinite number of terms, you will get the exact solution. If you are doing a smaller set, you are getting approximate solution. But if you keep on adding terms, you will get more and more accurate solution. That part being over. Number two is, why do we need the weight? Okay, in terms of general weighted residual method. So whatever this residual might be, you see, if I'm getting an approximate solution, there is no way this residual is going to be zero everywhere. Okay, for example, with a uniformly distributed load on a bar, okay, if you try to get a solution such like this, U equals C1x. So this x is your phi 1. And what is phi 0? Phi 0 is 0. To satisfy the essential boundary condition that u is 0 at x equals 0. Therefore, I'm making phi 0 equals 0. And phi 1 is x. Okay. And let's say there is a non-zero uniformly distributed load, which basically means if you were to do an exact solution, you were supposed to get a quadratic curve. But obviously, through through this, you will get an approximate solution. Okay.
Yes, sir.
Now the problem is you cannot actually use this expression over here. You see, you are supposed to take double derivatives, and that makes it trivially zero. Okay. So, but then you can use it over here, and maybe you can find out the expression for C1. But you cannot, because you see the coefficient of C over here, it would be zero. The coefficient of C1 should be zero. Okay. So that problem is there. You cannot use C1x. You cannot use linear bar. But then again, think about it. If Q is linearly changing, Q is a linear function of x, then the exact solution is cubic. But if you choose it to be C1x plus C2x squared, which means phi 1 is x and phi 2 is x squared. Okay. And then you do this. So from this, you'll get solution for C1 and C2. Okay.
Yes, sir. Yes, sir.
So you'll have to do this twice. Okay. So that's why you are supposed to multiply with the weight and do an integration. So that way you get one algebraic equation involving C1 and C2. Next, if you take the second weight, you will get a different equation. Now, as you can see that even from the concept of basic Taylor series, if I keep on adding terms up to infinity, I'm supposed to get the exact solution. Okay, for any arbitrary q. Okay, but here by truncating terms up to quadratic, I'm only allowing approximate solutions beyond uniform q. Okay, if q is linearly varying, quadratically varying, sinusoidal, anything, okay, it is going to be an approximate solution. Okay, but that approximate solution, an approximate solution could be anything, right? I mean, that depends on how much is the error. There should be some means by which you want to bring down the error. Okay, so in this case, what you are doing is you are multiplying the residual with the weights. You cannot actually claim that this residual is zero everywhere between 0 to L. In order to get that solution, you'll actually have to do the closed form integration. I mean, you are exactly trying to not do that. You are trying to do an approximate solution. So what you instead do is try to set a set of algebraic equation that somehow minimizes this residual. So what you do is you take this equation, multiply with it with a certain weight, and the number of weighing functions, or the number of weight functions, should be same as the number of trial functions, and the count begins from phi 1. And with that, you will get n number of system of linear equations. Okay, and once you solve them from that solution, you get an you get the approximate solution that minimizes this weighted integral, sorry, that minimizes this weighted residual. Okay, and Galerkin's method is a special method where you are using the trial functions themselves as the weights. Okay, so today I don't think we can cover Galerkin's method. That is the next method that we want to cover. But for today's class, your second assignment, so imagine for a bar, Q is a linear function length is 1 meter, area of cross section is 10 to the power minus 4 meters squared, Young's modulus is 200 GPa. Okay, solve by two term Galerkin's method. Okay, which is this one. Compare the solution with the solution from quadratic bar element in Fe. So you need to solve it in two ways. One using Galerkin's method, the other one being finite element method, in which you'd use quadratic bar element. Okay, and compare the solutions, compare the answers. Okay, which means the values of u at L and u as a function of x. Okay, ঠিক আছে? So it stop here today. মনে হচ্ছে এটা করা যাবে?
ট্রাই করবো স্যার।
Okay, try karo and see you on Saturday. Okay, so I'm stopping the recording now, and